Hello viewers and welcome to the e-learning classroom. So today we'll be covering KCSE 2022 Physics paper 1. So we'll be looking at the marking scheme of 2022 Physics paper 1. So let's start with section A. So we can look at the first question in section A. Question 1A. State what is meant by area. Area is a measure of an extent of a given surface. That is a simple definition for area. Area is a measure of extent of a given surface. Question B. State the SI unit of area. State the SI unit of area. So the SI unit of area is square meters, or the square meter, square meter in singular and in ones. Question 2. Explain why water in a glass tube forms a concave meniscus. Why water in a glass tube forms a concave meniscus. So the adhesive forces between water and glass molecules are higher than cohesive forces between water molecules. Adhesive force between water and glass molecules are higher than cohesive forces between water molecules. Question 3. Figure 1 shows how water is drawn from a large tank into a low-lying container using a rubber. Figure 1 shows how water is drawn from a large tank into a low-lying container using a rubber. Explain how the process takes place. Water is removed or sucked from the tube, lowering the air pressure in the tube below atmospheric pressure. The greater atmospheric pressure acting on the liquid surface on the upper container forces the liquid to flow into the lower container. So the first thing is that you have to suck the air from the glass tube, or from the tube, You have to suck the air from the tube. That is to lower the air pressure inside the tube, and then water will rise through the tube, and then now the water will continue flowing into the lower container due to pressure difference. So let's go to question 4. State how a piece of paper can be used to demonstrate that matter is made up of tiny particles. State how a piece of paper can be used to demonstrate that matter is made up of tiny particles. So the paper is cut into smaller and smaller pieces, hence showing that matter is not continuous, but is made up of tiny particles. The paper is cut into smaller and smaller pieces, hence showing that matter is not continuous, but is made up of tiny particles. Question 5. Figure 2 shows 6 is a maximum and minimum thermometer. Figure 2 shows 6 is maximum and minimum thermometer. Explain how increase in temperature causes index A to move upwards. Increase in temperature causes index A to move upwards. Explain. So increase in temperature causes the alcohol in P to expand, pushing up the mercury in right hand side, hence pushing index A upwards. So we've said increase in temperature causes the alcohol in P. Remember, P is the one that is full of alcohol, whereby we have the bulb at P. At point P we have the bulb. So you realize that when the air is heated, or when there is a change in temperature, you realize that liquid in P is the one that expands, because P is the bulb. And now when it expands, you realize that mercury will rise up on side A and go down on side B, because it will be pushed by the alcohol in P, and therefore now index A is pushed up by the mercury at that point. Question 6. State the difference between heat and temperature. 1. Heat is a form of energy that flows from a region of higher temperature to a region of lower temperature, while temperature is the degree of hotness or coldness of a body. That is in terms of definition. Heat is a form of energy that flows due to temperature difference, while temperature is the degree of hotness or coldness of a body. The second difference, SI unit. So SI unit of heat is Joule, while SI unit of temperature is Kelvin. Then the third one is in terms of measuring instruments. We have heat as no particular measuring instrument, but temperature is measured accurately using a thermometer. Those are the three major differences between heat and temperature. Let's go to question 7. State two factors that affect the stability of a cylindrical container. Factors affecting stability: 1. Base area of the cylinder. 2. Height of the position of COG above the base. That is the base area, and then the height of position of COG above the base. Question 8. Figure 3 shows a setup in which a spring with a pointer is attached to a wooden strip that has a hanging hook. A graph paper is fixed along the strip to be used to calibrate the spring. So we have the spring and we have a graph paper. A mass of 100 grams is provided. Explain how the spring balance can be calibrated. How you can subdivide the scale on the graph paper. So the first procedure, the first step, record the initial reading of the pointer when no mass is suspended from the hook of the spring has 0 gram. Record the initial reading of the pointer when no mass is suspended from the hook of the spring as 0 gram. Step 2. Suspend the 100 gram mass on the hook and mark the new pointer reading as 100 gram. So you have the initial reading 0 gram, the point where there is no mass hanged. You have the new reading 100 gram, the new pointer reading when it's carrying 100 gram. Step 3. Count the number of divisions between 0 and 100 gram, then subdivide and label accordingly. You subdivide the scale now into appropriate values. Let's go to question 9. Water enters a pipe at a velocity v1 at a point where the cross-sectional area is a1. It leaves the pipe at a velocity v2 at a point where the cross-sectional area is a2. Show that a1 v1 is equal to a2 v2. Show that a1 v1 equals a2 v2. We have area 1 velocity 1 and we have area 2 velocity 2. So we know volume flux is constant. In other words, the flow rate of a liquid is always constant. That means the volume over time is constant, which is the flow rate. Volume over time is constant. But we know volume of a liquid in a pipe of flow, in a tube of flow or a pipe of flow, is given by cross-sectional area times length. That means cross-section area 1 times length 1 over time is equals cross-section area 2 times length 2 divided by time. But we all know length over time. In other words, length is distance. Length over time or distance over time, that is velocity. And that means area 1 times velocity 1 is equal to area 2 times velocity 2. So that's how we show that area 1 velocity 1 equals area 2 velocity 2, whereby we are saying area 1 velocity 1 is flow rate or volume flux for part 1, and then area 2 velocity 2 is flow rate or volume flux for part 2 of the liquid. Let's go to question 10. Sketch the displacement time graph for a body moving with a decreasing velocity. We know the slope of displacement time graph represent velocity. Slope is velocity. That means the slope should be decreasing. And of course now you can see the graph. Of course, when the slope is decreasing, it will be curving as shown. That means the slope should be decreasing because the slope is now the velocity. In other words, that is a curve of deceleration. It's a deceleration curve. Let's go to question 10. Figure 4 shows a graph of force against time when a tennis ball is hit. Figure 4 shows a graph of force against time when a tennis ball is hit. You can see the graph there, force against time. Determine the mass of the tennis ball whose velocity is 60 meters per second. Assume the ball is stationary before it is hit. The mass. Of course, we know area under that graph will represent the impulse. Area under force time graph is impulse. That means we get the area, which is half base times height, which gives us 125 newton second. Then we know impulse Ft is change in momentum, mv minus mu. Impulse, that is from Newton's second law of motion. We know Ft equals mv minus mu, but we are told the ball is stationary before it was hit. That means mu is 0 because initial velocity is 0. And that means now the mass becomes 2.0833 kilogram. That is when you calculate the mass through the Newton's second law. Let's go to question 12. State the energy transformations that take place as a pendulum bob swings. Energy transformations that takes place as a pendulum bob swings. So pendulum, when you lift the pendulum here, you gain the pendulum bob as potential energy. Then when you release, the potential energy is converted to kinetic energy, and then remember it will go all the way to the upper side. On the other side, then it has potential energy there, and then it comes back. So it will be potential energy to kinetic energy to potential energy to kinetic energy to potential energy to kinetic. It will be alternating like that. That means you may choose one: potential energy to kinetic energy to potential energy. That is from the upper point to the middle to the upper point on the other side. Those are the energy transformations. Let's go to question 13. When determining the specific latent heat of fusion of ice by electrical method, other than mass, voltage, and current, state one other measurement that should be taken. When determining the specific latent heat of fusion of ice by electrical method, other than mass, voltage, and current, state one other measurement that should be taken. We know the formula MLF is equals, because we are determining current and voltage, so it means it will be power times time. So that means it will be current times voltage times time, because you are looking at what is losing the heat and what is gaining the heat. The heater is the one that is heating the ice. That means the heat gained by ice is MLF, mass times latent heat of fusion, heat to melt the ice. But now we also know heat supplied by the heater, because heat gained is equal to heat supplied, is given by current times voltage times time, which is power times time. So in other words, what are the readings? Mass, you already given in the question. LF is the one we are looking for, specific latent heat of fusion. Current is given. Voltage is also given. So that what is remaining is time. So the other quantity you measure there is time. So that's all about section A, 25 marks. So let's go now to section B, 55 marks. So let's start with the first question, 14A. State the Boyle's law. State the Boyle's law. So it states that pressure of a fixed mass of a gas is inversely proportional to its volume, provided that temperature is kept constant. pressure of a fixed mass of a gas is inversely proportional to its volume, provided that temperature is kept constant. So in other words, you are saying pressure is inversely proportional to volume. In other words, the smaller the volume, the more the pressure. And that one, to understand Boyle's law, PV, that is pressure against volume, just compare a balloon. What would happen if you compress a balloon between your two hands? If you compress the balloon, you realize that the balloon will burst. Why does it burst? That means that when you compress the balloon, you are reducing the volume, and therefore the pressure is increasing. That's why now the balloon is bursting. If you compress a tube, the tube, for example, when a vehicle is carrying a lot of load and the tire is compressed such that the tube which is having the air is very, very much compressed, you realize that the tube will burst. Why does it burst? Because you are saying now when you reduce the volume, the pressure increases. In other words, pressure is inversely proportional to volume. That is what we mean by Boyle's law. Let's go to part B, 14b. Figure 5a shows a column of hair of length 6 cm trapped by a mercury thread in a tube. Figure 5b shows the same tube in a horizontal position. So you can see the mercury thread, we have hair column, we have the test tube there, vertical and then horizontal. Draw the mercury thread in figure 5b. So you're going to draw the new mercury thread in 5b when it is now slanting or when it's in the horizontal position. So you realize that when it is vertical, the column of trapped hair is less than when it is horizontal. That means now the drop, the mercury thread should be towards the upper end, the opening, towards the opening. So the column, the length of trapped hair is larger. So you draw towards the opening. Then explain why the thread appears in 14b Roman 1. So we know from Boyle's law, P1 V1 equals P2 V2. Pressure 1 volume 1 is equals pressure 2 volume 2. But pressure 1 is bigger than pressure 2. Remember, pressure 1 is the pressure of the trapped hair. The pressure of the trapped hair. That means the trapped hair in figure 5a is having, in 5a, the trapped air is having a pressure of H rho g plus atmospheric. We have atmospheric from the upper end and the H rho g because of the weight of mercury thread acting downwards, compressing the hair. That means we have H rho g plus atmospheric. But in B you realize that now the only pressure acting against the trapped hair is atmospheric, because the weight of the BD, the mercury thread is acting downwards, so it's not affecting the trapped hair. That means now the pressure of the trapped air is equal to atmospheric, because they are countering each other. And it's important to understand, if you want to understand more on B, consider, for example, if you heat the hair, the trapped hair, what would happen? You realize that the mercury thread would be coming outwards. In other words, if you hold the balloon with warm hands, the mercury thread would be coming outwards, meaning you are increasing the pressure of the trapped hair. If you cool the trapped hair, the mercury thread will be coming inwards, meaning now you are lowering the pressure of the trapped hair. In other words, you realize that there is a balance of pressure between the atmospheric and the trapped hair. That's why we are saying the pressure of the trapped hair is equal to atmospheric pressure in B, 5b. In other words, pressure 1 is bigger than pressure 2, because pressure 1 is atmospheric plus H rho g, while pressure 2 is only atmospheric. But if pressure 2 is less, then definitely volume 2 will be bigger than volume 1, because pressure 2 is less. That means volume 1 is bigger, because from Boyle's law, P1 V1 is equals P2 V2. In other words, pressure times volume is constant. Let's go to question C. State what is meant by absolute zero temperature. Absolute zero temperature. So it means Absolute zero temperature is the temperature at which the volume of an ideal gas is assumed to be zero. The volume at which the volume of an ideal gas is assumed to be zero. Another definition is the lowest temperature that an ideal gas can reach. The lowest temperature that an ideal gas can reach, of course, that is self-explanatory. Let's go to Roman 2. A balloon contains hydrogen gas at a temperature of 2 degrees Celsius and a pressure of 6 millimeters of mercury. Determine the pressure in the balloon when the temperature is raised to 80. We have temperature 1 and temperature 2, and we also have pressure 1. So we are trying to find pressure 2. That means that is a pressure law. So it means P1 over T1 equals P2 over T2 from pressure law. P1 over T1 equals P2 over T2. The only thing here is that you have to work with the SI units. For temperature, you have to work with Kelvin. So that means you convert 2 degrees by adding 273. It becomes 275. So 6 over 275 equals pressure 2 over 353, whereby we are saying 80 plus 273. Because when you are converting Celsius to Kelvin, you add 273. So that is the only thing is that you convert the temperature to SI units, then you just replace the values. So pressure 2 becomes 7.702 millimeters of mercury. Let's go to question 15a. State 2 ways in which the centripetal force acting on a body of mass m can be reduced. 2 ways in which the centripetal force acting on a body of mass m can be reduced. To reduce centripetal force, we know centripetal F is given by mv squared over r. That is our centripetal force, mv squared over r. That means factors. Of course, you cannot reduce the mass, so that means you will vary the velocity or the speed of rotation, and then you can also, because you want to reduce centripetal, so you reduce the speed of rotation or the velocity, linear velocity. Alternatively, you increase the radius of the circular path. Increasing the radius of the circular path or reducing the speed of rotation. Let's go to 15b. A stone of mass 0.5 kilogram tied to a string is whirled in a vertical plane along a circular path of radius 2 meters. What is its frequency? And that its frequency is 2 cycles per second. Let's read that question again. A stone of mass 0.5 kilogram tied to a string is whirled in a vertical plane along a circular path of radius 2 meters. That means that this is a motion in a vertical circle. You're given the mass of the stone and the radius of the circular path. And that its frequency is 2 cycles per second. And we also given the pi. Determine, Roman 1, the velocity of the stone. That is the linear velocity. We know linear velocity is given by omega r. V equals omega r. But because we do not have omega and we have pi and frequency, omega is 2 pi f. Omega is given by 2 pi f. Omega is 2 pi f. That means 2 pi f times radius. Then you replace the values. 2 times 3.142 times frequency, which is 2 cycles per second, times the radius, which is 2 meters. Then you get the answer is 25.136 meters per second. Let's go to Roman 2. Tension in the string when the stone is at the topmost part of the circular path. At the topmost part, we know tension is given by centripetal minus weight. At the topmost, mv squared over r minus mg. That means you replace the values. Mass is 0.5 kilogram. Linear velocity, we calculated there, 25.136 squared, then divided by radius is 2 meters, minus mg 0.5 times 10. That is centripetal minus weight at the topmost part, which gives you tension is 153 meters at the topmost part. State with reason how the tension in the string changes as the stone gets to the bottom of the circular path. How tension changes at the bottom of the circular path. At the bottom, remember, tension is given by centripetal plus weight. We have seen that the top is minus, at the bottom is plus, addition. So that means tension increases because at the bottom, tension is given by centripetal plus weight. In other words, tension and weight are acting in the same direction. Let's go now to question 16a. Figure 6 shows a cube of mass 2 kg and science 5 cm fully immersed in a liquid of density 0.8 gram per cubic centimeter. Figure 6 shows a cube of mass 2 kg and science 5 cm fully immersed in a liquid of density 0.8 gram per cubic centimeter. The cube is balanced by a stone of mass m. You have the stone, we have the cube. You can see the balanced system. Given that the gravitational field strength G is 10 Newton per square meter, determine the Roman 1 half thrust acting on the cube. Remember, half thrust is always equal to the weight of the fluid displaced. That means half thrust will be given by rho Vg. Half thrust is rho Vg. Density is 0.8, so to be 800 in SI units. 800 volume, length times width times height. That means 5 times 5 times 5, but in SI units. 0.05 meters times 0.05 meters times 0.05 meters, then G is 10. The key thing to note here is that when something is fully immersed in a liquid, then definitely volume of the solid is also equal to the volume of liquid displaced, because this solid is fully submerged, and that means now that if it is fully submerged, the volume of the solid must be equal to the volume of liquid displaced. That means volume, you just take the volume of the cube, then density of the liquid times volume of the cube times G. You get 1 Newton half thrust. Apparent weight. We know apparent weight is the real weight minus half thrust. That is the weight in air minus half thrust. So, and in that case, weight in air, the real weight is, we are told that the mass of that solid is 2 kg. So that means the real weight is 2 times 10. Then minus half thrust, which we have got there, is 1 Newton. So 2 times 10, 20 minus 1, which gives you 19 Newton. That is the apparent weight. Then we are told to find the weight of the stone. So we have got the apparent weight on the right hand side, weight of the stone on the left hand side. So we know weight of the stone, you get now the principle of moments. Force 1 d1 equals force 2 d2. Force 1 is there now there, the apparent weight. So 19 times 20 centimeter, but in meters you can work with 0.2 meters, is equals force 2, which is the weight of the stone, times 50 centimeters. Then you get force 2 is 7.6 Newton. Mostly you can work with SI units to be on the safer side. Let's go now to part B. To B, a block of mass 500 gram floats in water. A block of mass 500 gram floats in water. Determine the volume of the block under the water. Then you also given density of water is 1 gram per cubic centimeter. This is the law of flotation. We know a floating object displaces its own weight. A floating object displaces its own weight. That means half thrust is equal to the weight of the solid. Half thrust is rho Vg. Rho is 1000 Volume, we do not have, G is 10, is equals mg, 0.5 kilogram times 10. Then you get a volume is 2000 cubic meters. Let's go now to the next question, that is 17a. State two factors that affect the boiling point of a substance. Two factors that affect the boiling point of a substance. Of course, the first one is the presence of impurities, and then we have the pressure. Presence of impurities. For example, you add salt to the water boils at a higher temperature. For example, you cover water in a sufuria when it is in the when it's boiling in the fire. You cover water, and you realize that the boiling point is raised because the steam will accumulate and then pressure will build up. So we are saying the factors, we have the pressure and the presence of impurities. Part B, a well-lacked calorimeter contains a liquid of mass 200 gram at a temperature of 10 degrees Celsius. That means we have a calorimeter and a liquid inside at 10 degrees. Also meaning the temperature of calorimeter is also the same as 10. An electric heater 8 watt is used to heat the liquid. Figure 7 shows a graph of temperature against time for the liquid. We have the graph here, temperature against time. From the graph, determine the boiling point of the liquid. If you look at the graph, it is starting from 10, that's the initial temperature, then it's building up to a particular value which is 104. 104. Remember, each division is representing two units, because you have 10 units, 5 units representing 10. Each 5 units are representing 10 degrees Celsius. That means we have 104 degrees Celsius, that's the boiling point. Then Roman 2, quantity of heat given out by the water between time t 1 minute and time t 4.5 minute. Quantity of heat given out by the heater between 1 minute and 4.5 minutes. We know for the heater what we have the power. The power of the heater we are given, it is 8 watts. That means heat is given by power times time, because we already have the power for the heat and we have been given time here now. Heat is power times time, so it is 8 watts multiplied by 4.5 minus 1 is 3.5, but now in seconds times 60. So 80 times 3.5 times 60, you get 16,800 joule. Always work with the SI units. Let's go to part C. Based on B Roman 2, determine the Roman 1 temperature change between T1 minute and T 4.5 minutes. Temperature change, of course that one you can read directly from the graph. 4.5 minutes to 1 minute. Let's say 4.5 minutes, the temperature. So that is 94 degrees. Then 1 minute we have 28 degrees. So 94 minus 28, you get 66 degrees Celsius. That is a change in temperature from the graph. Then Roman 3, specific heat capacity of the liquid. Specific heat capacity of the liquid. So we know heat supplied is always equal to the heat gained. That means MC change, the heat supplied is equals to MC change in temperature. In other words, 16,800, which was the heat supplied by the heater, is equals heat gained by the liquid, MC change in temperature. That means 16,800 equals mass 0.2. That is the mass of the liquid, because we are given it is 200 gram. So 0.2. Specific is the one we're looking for. Change in temperature, we got it in Roman 1. 94 minus 28, which is 66 degrees. So you multiply with what you got in Roman 1. So that means specific now will be 1272.73 joule per kilogram per Kelvin, because heat supplied is equals heat gained. So heat supplied by the heater, the same as the liquid heat gained by the liquid. Then you replace the values and then you get what you do not have. So we go to number D. 2 grams of vapor was collected from the liquid between T 5.4 minutes and T 6.3 minutes. That means we have vaporization now, the boiling point. We have the boiling or the vaporization 5.4 minutes to 6.3 minutes. Determine the specific latent heat of vaporization of the liquid. Specific latent heat of vaporization. That's the 5.4 is at the boiling point, and also 6.3. They are all at the boiling point. That means the heat supplied by the heater for that time is equals heat gained by the liquid at that time also. So heat supplied by the heater. For the heater, we already have the power, so we just require time because it is PT, because that's electrical power. So 80 times time, PT time will be, if you subtract between, we are taught time 5.4 minutes to 6.3 minutes. That means if you subtract 6.3 minus 5.4, you get 0.9 minutes. 0.9, but now in seconds, 0.9 times 60. That is a power times time. 80 times 0.9 minutes times 60 to convert to seconds as the heat supplied by the heater for that time. Between that time 5.4 to 6.3 is equal to heat gained to vaporize the liquid. The heat gained to vaporize is normally given by MLV. That means heat supplied PT equals heat gained MLV. Mass is already 0.002 because you have 2 gram. You convert to SI units, 0.0002 kilogram times LV. Then you get the value of specific latent heat of vaporization is 2.16 times 10 raised to times 10 raised to power 6 joule per kilogram. Joule per kilogram. So let's go now to the last question, question 18. A weighing balance, 18A, a weighing balance placed on the floor of a lift is used to measure the weight of a body of mass 80 kg. Determine the reading on the balance when the lift moves upwards. So we have a weighing balance, and then the lift is moving upwards with a Roman 1 with uniform velocity. So that means when the lift is moving upwards with uniform velocity and you are measuring the weight of a body of mass 80. So with uniform velocity, it means the reading of the spring balance in the lift will just be the normal reading, the normal weight, because there is no acceleration. That means weight is mg. So 80 kilograms times 10, which is 800 Newton. That's the weight of the body, the reading, or the normal reaction, the reaction of that body on the lift. Roman 2, with acceleration 3, the lift is accelerating, and it is also moving upwards. So if the lift moves upwards, then the body becomes heavier. If the lift is accelerating, the body becomes heavier. That means the reading, the reaction will be weight, the normal weight, plus MA. Remember from Newton's second law, force can also be given by MA, mv minus mu all over t, which is MA. That means mass times acceleration, because the lift is accelerating. So mass is 80, the acceleration is 3. So that means the lead weight 800 Newton plus the new force that comes from acceleration of the lift, which is mass now of the body, 80 times acceleration of the lift, which is 3, because the acceleration of the lift is the same as the acceleration of the body inside the lift. So 800 plus 80 times 3, which is 240. Then you get 1040 Newton. 1040 Newton. B. Explain why a person studying on a boat. Before we go to that B, it's important to note that when a lift goes downwards with uniform speed, the reading of the spring balance is the normal weight of the body. But if the lift is accelerating downwards, then the body becomes lighter. That means the normal reaction will be mg minus ma. In other words, the normal weight of the body minus the force due to acceleration of the lift. So upward, the body is heavier, so you add mg plus ma. Downwards, the body is lighter, so you subtract mg minus ma. Remember, if the acceleration of the lift is equal to the acceleration due to gravity, if the acceleration of the lift is equals to acceleration due to gravity, in other words, if g equals a, then the body becomes weightless. The weight becomes zero, the reaction. In other words, if g is equal to a, it means mg minus ma will be equal. So mg minus, it's like saying 10 minus 10, which will be 0. So that's what we're saying. If the acceleration of the lift and the pull of gravity are equal, then the body becomes weightless. Let's go to part B. Explain why a person standing on a boat is likely to fall into the water when attempting to jump to the shore. Explain why a person standing on a boat is likely to fall into the water when attempting to jump to the shore. So the person exerts a backward force on the boat, and due to the less friction between the boat and the water, the boat slides backwards, hence reducing the forward force of the man, which in turn makes the man fall into the water. So what we are saying essentially, as the person jumps from the boat which is on the water, the boat will slide backwards because viscosity is less, friction in liquid is less. So the boat slides backwards, and that means the forward thrust of the man will be reduced. In other words, the man will fall into the water because as the boat slides backwards due to less friction between boat and water, then even the forward push of the man will be reduced, making the man fall into the water. Let's go to part C, the very last question. A box is moved 30 meters long, or a box is moved 30 meters along a surface whose frictional force is 1000 Newton with a uniform velocity. A box is moved 30 meters along a surface whose frictional force is 1000 Newton with uniform velocity. Determine the work done against friction. So you're given the force, you're given the distance, you don't find work done against friction. It's important to note, if a body is moving with uniform velocity, then it means the force you are applying is used to overcome friction. If a body is moving with uniform speed, then the force you are applying to move that body is used to overcome friction. In other words, the forward force is the one you are applying. The backward force is friction, which are equal. Because if the forward force is larger, the body should accelerate. Because we know there is a force given by ma, mass times acceleration. So anytime there is acceleration, there is a force involved. But we are saying if the acceleration is 0, for this case, because the body is having uniform velocity, if acceleration is 0, then the force applied is used to overcome only friction. That means now work done against friction is Fd, where friction is 1000 Newton, because we are saying the forward force is equal to friction backward force. So 1000 times distance, which is that, then you get 30,000 joule. So that is physics paper 1 2022 KCSE, and that is what was expected of you. You realize that many concepts were tested, so you can be able to check the topics tested and also the concepts that were tested in every topic. But the paper was very simple, but you needed to be careful now you're answering the questions, because now of the technicality of some of the answers required. So that marks the end of today's session. Let's see you in the next video. Thank you.